If you were to travel in a straight line toward the center of our galaxy, the journey would take you roughly 26,000 years, even moving at the speed of light. You would pass through the outer spiral arms, through the thin disk of stars and gas that makes up most of what we call the Milky Way, and eventually into a region that grows steadily more crowded, more active, and more extreme with every light year you covered. At the very end of that journey, you would arrive at a place unlike anywhere else in our galaxy, a dense, turbulent, ancient region of space where stars are packed thousands of times more tightly than in our own neighborhood, where gas clouds move at extraordinary speeds, and where gravity is so intense that it shapes everything for light years in every direction. At the heart of that region sits Sagittarius A-star, a supermassive black hole, the anchor of our galaxy. Tonight we will come to understand it, what it is, how we know it exists, and what its presence tells us about the universe we inhabit. Get comfortable. We have a long and quiet journey ahead of us. This is Sleepy Time Universe, where we explore the cosmos at a pace designed for rest and reflection. Chapter 1. Introduction to the Galactic Center. To understand Sagittarius A-star, we first need to understand where it lives. And where it lives is a place that most people, even those with a deep interest in astronomy, rarely think about in detail. We tend to think of our galaxy as a broad, flat disk of stars, a pinwheel shape seen from above, with long spiral arms curving outward from a central hub. That image is accurate in its broad strokes, but it leaves out almost everything that makes the center of the Milky Way so extraordinary. The galactic center is not simply a denser version of the rest of the galaxy. It is a fundamentally different environment. The density of stars there is staggering. In our own part of the galaxy, the nearest star to our Sun is Proxima Centauri, about 4 light years away. 4 light years of mostly empty space separating us from our closest neighbor. At the galactic center, that kind of distance between stars does not exist. Stars there are, separated by distances measured in light days or even light hours. The night sky, as seen from a planet near the galactic center, would blaze with thousands of stars bright enough to cast shadows. There would be no true darkness at night. The sky would glow continuously, lit by the combined light of millions of densely packed suns pressing in from every direction. But the stars themselves are only part of the story. The galactic center is also filled with enormous clouds of gas and dust, some of them actively forming new stars, others being torn apart by the intense gravitational and magnetic forces that permeate the region. There are vast structures of ionized gas stretching across dozens of light years. There are supernova remnants, the expanding shells left behind when massive stars reached the ends of their lives and exploded, layered on top of one another, like the rings of a very old and complicated tree. There are magnetic filaments, narrow threads of magnetized plasma that run perpendicular to the galactic plane and extend for hundreds of light years, structures whose origin is still not fully understood by the astronomers who study them. And underlying all of it, shaping everything, is gravity, an enormous, centralized gravitational pull that draws everything in the galaxy, over the course of billions of years, toward a single point. Not evenly, not uniformly, but consistently and relentlessly. The galaxy rotates around that point. Every star, every cloud of gas, every remnant of every explosion that has ever occurred in the Milky Way participates in that rotation. And at the center of it all, providing the gravitational anchor that makes the whole structure possible, is Sagittarius A-star. For most of human history, we knew none of this. The galactic center was simply a direction in the sky, toward the constellation Sagittarius, low on the horizon for observers in the northern hemisphere during summer evenings. Ancient astronomers could see that the band of the Milky Way was brightest in that direction, that the density of stars increased as you looked toward Sagittarius, and that something lay beyond the visible stars in that direction. But they could not see what. The dust and gas between us and the galactic center absorbs visible light almost completely. A photon of visible light trying to travel from the galactic center to Earth would have to pass through the equivalent of 30 magnitudes of extinction. That number has a precise meaning in astronomy, but the simplest way to appreciate it is this. For every 100 billion photons of visible light that begin the journey from the galactic center toward Earth, roughly one arrives. The rest are absorbed or scattered by the intervening dust before they can reach us. The galactic center is invisible light, essentially invisible from where we stand. This invisibility protected the secrets of the galactic center for a very long time. It was only when astronomers developed the ability to observe in other parts of the electromagnetic spectrum, particularly radio waves and infrared light, which pass through the intervening dust far more easily than visible light does, that the true nature of the galactic center began to reveal itself. And what it revealed, piece by piece over several decades of patient observation, was stranger and more compelling than almost anyone had anticipated. The distance to the galactic center is itself worth pausing on. 26,000 light years. A light year is the distance light travels in 1 year, approximately 9.5 trillion kilometers. Multiply that by 26,000, and you have a number so large that it resists any attempt at genuine comprehension. We can say the words, we can write the figures, we can even do the arithmetic, but the actual distance involved is beyond anything our everyday experience can meaningfully anchor. The farthest any human being has ever traveled from Earth is the distance to the Moon, roughly 380,000 kilometers. The galactic center is more than 60 billion times farther away than that. And yet astronomers have not only detected something at that distance, they have measured it, studied it, imaged it, and built up a detailed and remarkably complete picture of what it is and how it behaves. That is in many ways the deeper story running beneath everything we will discuss tonight. Not just what Sagittarius A-star is, but how we came to know it, how human ingenuity, patience, and technological creativity allowed us to reach across 26,000 light years and draw back a curtain that nature had kept firmly closed for the entire history of our species. The galactic center sits in a region of the sky that lies in the direction of the constellation Sagittarius, which is best visible from Earth's southern hemisphere and from low northern latitudes during the summer months. Even without knowing what lies there, that part of the sky has a special quality to it on a clear, dark night. The Milky Way is noticeably broader and brighter in that direction, the star fields denser, the textures richer. Our ancestors noticed this too, and many cultures associated that region of the sky with special significance, though none could have known why the sky was brighter there, or what lay at the center of that brightness. Now we know, and what we know is extraordinary enough to spend a long, unhurried evening exploring in careful detail. The galactic center region is usually defined as the inner few hundred light years of the Milky Way, a small fraction of the galaxy's total extent of roughly 100,000 light years, but a region that contains an outsized share of the galaxy's interesting physics. It is home to some of the most massive and luminous star clusters in the galaxy. It contains some of the densest molecular clouds anywhere in the Milky Way. It hosts magnetic structures that have no clear analogue elsewhere in the galaxy. And at its very heart, it harbours the supermassive black hole that we will be exploring throughout this evening. One of the things that makes the galactic center particularly challenging to study is not just the dust that blocks visible light, but the sheer complexity of everything that is happening there. In our own part of the galaxy, space is relatively quiet. There are stars separated by vast distances, and between them there is mostly nothing. Thin wisps of gas and dust, the occasional nebula, the quiet background of interstellar space. The galactic center is nothing like that. Every cubic light-year of space in that region is more interesting, more active, and more complicated than almost anything in our local neighborhood. Disentangling the different structures, understanding which processes are driving which observations, and building a coherent picture of the whole from the individual pieces. This is the challenge that galactic center astronomers face, and it is a challenge they have been working on for decades. The tools available for that work have expanded dramatically over the course of the 20th and 21st centuries. Radio telescopes opened the first clear windows onto the galactic center in the mid-20th century. Infrared observatories, both ground-based and space-based, followed and allowed astronomers to see individual stars through the dust for the first time. X-ray and gamma-ray observatories revealed the high-energy processes occurring in the region. And most recently, the Event Horizon Telescope produced the first direct image of the supermassive black hole itself, an achievement that required coordinating radio observatories across the entire surface of the Earth into a single instrument of extraordinary resolution. Each of these technological developments has opened a new chapter in our understanding of the galactic center, and each has revealed new questions, new puzzles, new unexpected structures, new phenomena that require new explanations. The history of galactic center astronomy is a history of surprises, of observations that did not fit existing models, of theories that had to be revised or discarded when the next generation of instruments looked more closely and saw something that had not been anticipated. That history of discovery is worth knowing because it shapes our current understanding in important ways. The picture we have today of Sagittarius A-star and its environment is not the picture that anyone set out to find. It emerged gradually and sometimes unexpectedly from decades of observations that each added a new piece to the puzzle. Understanding how we know what we know about the galactic center is as important as understanding what we know. We will spend the next chapter tracing that history, the long and sometimes surprising story of how astronomers first detected Sagittarius A-star, then understood its nature, and finally confirmed it beyond reasonable doubt as a supermassive black hole at the center of our galaxy. But before we move on, take a moment to simply sit with the image of the galactic center as we have described it so far. A region of space 26,000 light-years away, hidden behind curtains of dust and gas, containing some of the most extreme and interesting structures in the entire Milky Way. A place where stars are packed so tightly that the night sky would never be truly dark, where gas moves at hundreds of kilometers per second, where magnetic fields thread through everything, organizing and shaping the material around them in ways we are still working to understand. And at the very center of all of it, invisible to ordinary light, but revealed by radio waves and infrared radiation, and ultimately, by the direct image produced by a telescope the size of the Earth. A supermassive black hole, patient and ancient, holding the galaxy together. That is where we are going, tonight. And we have all the time in the world to get there slowly. There is something quietly remarkable about the fact that the center of our own galaxy was, until very recently, one of the most mysterious places in the universe as far as human knowledge was concerned. We live inside the Milky Way. We are part of it. Our sun is one of its several 100 billion stars, orbiting at a comfortable distance from the center, in one of the galaxy's outer spiral arms. And yet, for the vast majority of human history, we had no idea what lay at the heart of the structure we inhabit. The center of our own galaxy was more unknown to us than the surfaces of distant planets, more obscure than the composition of stars thousands of light years away. That obscurity was entirely due to the dust. Interstellar dust, tiny grains of carbon and silicate material, each far smaller than a grain of sand, fills the space between stars throughout the galaxy, but is particularly concentrated along the galactic plane. Light traveling through the galactic plane is absorbed and scattered by this dust, with shorter wavelengths affected more strongly than longer ones. Blue light is scattered almost immediately. Red light travels farther before being absorbed. And visible light of any color, trying to travel the full 26,000 light years from the galactic center to Earth along the galactic plane, is almost entirely absorbed before it arrives. This is why the galactic center looks, to the naked eye, like a region of relative darkness rather than brightness, even though it contains more stars per cubic light year than almost anywhere else in the galaxy. The dark lanes and patches visible in the Milky Way on a clear night are not holes in the galaxy, but dense clouds of dust that block the light of the stars behind them. The very richness and density of the galactic center is hidden behind a veil of intervening material, making it appear, paradoxically, less bright than the star fields on either side. Radio waves and infrared radiation cut through this veil with relative ease. Radio waves, with their long wavelengths, are barely affected by interstellar dust at all. They pass through it almost as if it were not there. Infrared radiation, with wavelengths longer than visible light but shorter than radio waves, is also far less affected by dust than optical light. It was through these two windows, radio and infrared, that astronomers first began to see the galactic center clearly, and it was through these two windows that the evidence for Sagittarius A-star first accumulated. The transition from ignorance to knowledge about the galactic center happened gradually over the course of several decades in the mid to late 20th century. It did not happen in a single dramatic moment of discovery. It happened through the accumulation of many observations, each adding a small increment of understanding, each raising new questions that motivated the next round of observations. This is how science usually works, not in sudden leaps, but in a slow and steady climb, each step building on the last. As you settle into this exploration, it is worth appreciating that slow climb for what it is. The story of Sagittarius A-star is not just a story about a black hole. It is a story about human curiosity and persistence, about the willingness to look carefully at something difficult and obscure, to develop the tools needed to see it more clearly, and to follow the evidence wherever it leads, even when it leads somewhere unexpected and strange. That story begins in earnest in the next chapter, where we will trace the history of discovery that brought us from the first radio detections of the galactic center to the Nobel Prize and the Event Horizon Telescope image. But it begins in a sense, with every astronomer who looked toward Sagittarius on a clear night and wondered what lay beyond the stars they could see. Chapter 2. Discovery of Sagittarius A. How we found it. The story of how we found Sagittarius A-star begins not with a dramatic discovery, but with a slow accumulation of evidence spread across several decades. It is a story that involves multiple generations of astronomers, a series of technological breakthroughs, and a gradual narrowing of possibilities until only one explanation remained. It is, in that sense, a very human story, one of patience, persistence, and the quiet satisfaction of understanding something that was previously unknown to anyone who had ever lived. The first hints came from radio astronomy. In the early 1930s, a radio engineer named Karl Jansky was investigating sources of interference affecting transatlantic radio communications at Bell Telephone Laboratories in New Jersey. His task was practical and unglamorous. Find out what was causing static in the long-distance radio signals his employer depended on, and if possible, eliminate it. To do this, he built a large rotating antenna mounted on a circular track, a structure that could be pointed in any direction, and that became known informally among those who worked with it as Jansky's merry-go-round. He used it to systematically map sources of radio noise across the sky, cataloguing everything he found and trying to identify its origin. What he found was unexpected, and in its implications, extraordinary. In addition to interference from thunderstorms and other terrestrial sources, there was a persistent signal coming from beyond Earth entirely. It was not coming from the Sun, though the Sun also produces radio emission. It was not coming from any identifiable source in the immediate vicinity. Instead, it appeared to come from a fixed direction in space, a direction that corresponded, when Jansky worked through the astronomy carefully, to the center of the Milky Way, to the constellation Sagittarius, to the very heart of our galaxy. Jansky published his findings in 1933 in a paper that described this cosmic radio emission carefully and accurately. But the significance of what he had detected was not immediately appreciated by the broader scientific community. Astronomy in the 1930s was still primarily an optical discipline, a science of visible light, of telescopes and photographic plates, and the careful analysis of stellar spectra. Radio astronomy was not yet an established field. The tools and techniques needed to explore what Jansky had found did not yet exist in any developed form, and there was no community of researchers equipped to follow up on his discovery in a systematic way. It would take another decade and a world war, and the subsequent explosion of radio technology that the war produced, before astronomers were able to return to the galactic center with instruments capable of learning more. The development of radar during the Second World War produced a generation of engineers and physicists with deep expertise in radio technology, and many of them turned their skills toward astronomy when the war ended. The result was a rapid flowering of radio astronomy in the late 1940s and through the 1950s, with new telescopes being built across Europe, Australia, and North America, and new techniques for analyzing radio signals being developed and refined at a remarkable pace. The galactic center emerged early as one of the most interesting and productive targets for these new instruments. Radio maps of the Milky Way began to reveal the structure of the galaxy in ways that optical astronomy had never been able to achieve, because radio waves, like infrared light, pass through the dust that blocks visible light, allowing astronomers to see all the way to the center of the galaxy and beyond. For the first time, the true scale and complexity of the galactic center began to come into view. What radio astronomers found there was a complex and energetic region unlike anything in the outer parts of the galaxy. There were large-scale structures of radio emission stretching across the central regions, filling hundreds of light-years with glowing gas and tangled magnetic fields. There were clouds of ionized gas moving at high velocities, their motions suggesting the presence of powerful forces at work. And at the very center of it all, there was a compact, bright source of radio emission, a source that stood out clearly from everything around it, whose brightness and compactness suggested it was something fundamentally different from the extended structures on either side. This central source was catalogued and studied through the 1960s and into the early 1970s, but its true nature remained unclear. Astronomers debated its origin and significance. Was it a cluster of radio-bright stars, too compact to resolve individually? Was it a region of particularly dense ionized gas, compressed into a small volume by forces not yet understood? Was it something else entirely, something that had no clear analogue elsewhere in the galaxy? The answer began to come into sharper focus in 1974, when two radio astronomers, Bruce Ballack and Robert Brown, used the Green Bank Radio Telescope in West Virginia to make a high-resolution observation of the galactic center at short radio wavelengths. What they found was a compact radio source with properties unlike anything else in the region. It was extremely bright for its size. It was extremely small in apparent angular extent, smaller than any extended gas cloud or star cluster could plausibly be at that distance. And its radio emission had a distinctive spectral shape that suggested it was something fundamentally different from the gas clouds and star-forming regions around it. Ballack and Brown named this source Sagittarius A-star, the asterisk in the name distinguishing it from a broader region of radio emission called Sagittarius A that had been identified and catalogued earlier. It was a naming convention rather than a declaration of the object's nature, but the name has stuck ever since, becoming one of the most recognizable designations in all of modern astronomy. But naming something and understanding it are very different things. In 1974, the nature of Sagittarius A-star was still deeply uncertain. The most natural explanation, given what was known about compact radio sources at the centers of other galaxies, was that it might be associated with a massive black hole. Theoretical work by astronomers, including Donald Lyndon Bell, had suggested in the late 1960s that supermassive black holes might be responsible for the energetic phenomena observed at the centers of active galaxies. The quasars and Seyfert galaxies that released extraordinary amounts of energy from very compact regions. Perhaps the center of the Milky Way contained something similar, though in a much quieter and less active state. But this was still speculation, unsupported by direct observational evidence. To confirm that Sagittarius A-star was indeed a supermassive black hole, astronomers needed more than a compact radio source. They needed to measure the mass of whatever was there, and to show that that mass was confined to a region small enough that only a black hole could account for it. Gathering that evidence would take the better part of 3 more decades. Through the 1980s and into the 1990s, observations of the galactic center improved steadily as new technologies became available. Infrared astronomy in particular opened up important new possibilities. Infrared detectors mounted on large ground-based telescopes could see through the dust that blocked visible light and image. Individual stars near Sagittarius A-star for the first time. What those images showed was increasingly suggestive of something extraordinary at the center. Stars near Sagittarius A-star were moving fast, much faster than stars elsewhere in the galaxy. The velocities implied by the measurements were so high that they could only be explained by an enormous concentration of mass somewhere nearby. And the most natural location for that mass was the position of Sagittarius A-star itself. Through the 1990s, two teams of astronomers made this problem the central focus of their research programs in what became one of the most productive scientific competitions in the history of astronomy. One team was based at the Max Planck Institute for Extraterrestrial Physics in Garching, Germany, and was led by Reinhard Genzel, a meticulous and deeply experienced observer who had been studying the Galactic Center for years. The other team was based at the University of California, Los Angeles, and was led by Andrea Ghez, a younger astronomer who brought fresh energy and new technical approaches to the problem. Both teams used the world's largest telescopes, initially the New Technology Telescope in Chile and the Keck telescopes in Hawaii, equipped with infrared cameras and later with the revolutionary technology of adaptive optics. Adaptive optics systems use rapidly deformable mirrors and real-time measurements of atmospheric turbulence to correct, in real time, for the blurring effects of Earth's atmosphere on incoming starlight. Before adaptive optics, ground-based telescopes were limited in the sharpness of the images they could produce by atmospheric turbulence, regardless of how large their mirrors were. After adaptive optics, the same telescopes could achieve images approaching the theoretical diffraction limit set by the diameter of their mirrors, a dramatic improvement in angular resolution that transformed what was observable. With these tools, both teams began tracking the positions of individual stars near Sagittarius A-star year after year. The task required extraordinary patience and precision. The stars were faint. They were packed closely together. They were surrounded by the bright, complex emission of the galactic center region. Measuring their positions precisely enough to detect the small annual shifts caused by their orbital motion required the most careful possible calibration of every instrument, the most rigorous possible correction for every source of systematic error, and the simple accumulation of year after year of careful observation. By the late 1990s, the first orbital arcs were beginning to emerge from the data. Individual stars could be seen moving, their positions shifting from year to year in ways that traced out portions of what were clearly elliptical orbits centered on Sagittarius A-star. By the early 2000s, several stars had been observed through enough of their orbits to allow meaningful constraints on the central mass. And by 2002, the star S2 had been observed through nearly a complete orbit, providing what was effectively a definitive measurement. The result was unambiguous. The mass required to produce the observed orbits was approximately 4 million times the mass of our Sun, and that mass was confined to a region smaller than the orbit of S2 itself, a region no more than a few hundred astronomical units across. There was only one known class of object that could pack 4 million solar masses into so small a volume. The conclusion was clear. Sagittarius A-star was a supermassive black hole. Both teams reached this conclusion independently, using different telescopes, different instruments, different analysis techniques, and different stars, and they reached the same answer. The convergence of two independent lines of evidence to the same result is one of the most powerful forms of confirmation in science, and in this case, it was decisive. The scientific community accepted the conclusion rapidly and without significant dissent. The debate about what Sagittarius A-star was had been running for 3 decades, and it was now effectively over. Reinhard Genzel and Andrea Ghez were awarded the Nobel Prize in Physics in 2020 for this work, a recognition that came nearly 2 decades after the key observations, reflecting both the time it takes for major discoveries to be fully absorbed and celebrated by the scientific community, and the Nobel Committee's preference for awarding prizes only after results have been thoroughly confirmed. Their prize was shared with the theoretical physicist Roger Penrose, who had made foundational mathematical contributions to our understanding of black holes earlier in the century, proving that singularities, the extreme endpoints of gravitational collapse, are an inevitable consequence of general relativity under very general conditions. The Nobel Prize was, in a sense, simply a formal acknowledgement of what the astronomical community had already long accepted. By 2020, the evidence for Sagittarius A-star as a supermassive black hole was not just strong. It was overwhelming, layered, and confirmed by multiple independent methods. The field had moved on to deeper and more detailed questions. Questions not about whether the object was a black hole, but about what kind of black hole, how it behaved, what its history had been, and what role it had played in shaping the galaxy around it. Those are the questions we will be exploring for the rest of this evening. But before we move on, it is worth pausing to appreciate the arc of the story we have just traced. From Karl Jansky, adjusting his rotating antenna in a New Jersey field in the early 1930s and noticing a faint persistent signal from the direction of Sagittarius, to 2 teams of astronomers spending decades tracking the motions of individual stars 26,000 light-years away. It is a journey that took the better part of a century and involved the contributions of hundreds of scientists, engineers, and institutions across many countries. Science moves at its own pace. It cannot be rushed beyond what the available evidence and technology will support. The story of Sagittarius A-star took as long as it took because each step required tools that did not yet exist, techniques that had to be invented, and observations that could only accumulate 1 careful year at a time. The result, a detailed, robust, multiply-confirmed understanding of the supermassive black hole at the center of our galaxy, was worth the wait. There is something worth dwelling on in the way this discovery unfolded, not as a single moment of revelation, but as a gradual convergence of evidence from many directions. The detection of a compact radio source by Barlick and Brown in 1974 was important, but it was not proof of a black hole. The infrared measurements of stellar velocities in the 1980s were suggestive, but not conclusive. The first orbital arcs traced in the late 1990s were compelling, but incomplete. It was only when the full orbit of S2 was measured, when the mass and its confinement to a small volume were established beyond reasonable doubt, that the case became truly definitive. This gradual convergence is characteristic of how major discoveries in astronomy tend to work. Unlike experiments in a laboratory, where conditions can be controlled and hypotheses tested directly, astronomical observations are always indirect. We cannot visit Sagittarius A-star. We cannot place instruments near it. We can only observe the light and radio waves and X-rays that reach us across 26,000 light-years of space and reason carefully about what must be producing them. That kind of reasoning, applied carefully and checked against alternative explanations, is how we know what we know about the universe. And the story of Sagittarius A-star is one of the finest examples of that process working as it should, slowly, carefully, and ultimately with extraordinary success. The discovery also depended on a kind of institutional patience that is itself worth appreciating. The observations that ultimately proved the existence of the supermassive black hole at the center of the Milky Way were not made in a single observing campaign. They were accumulated over more than 2 decades of continuous effort, requiring the commitment of telescope time, funding, and scientific attention year after year, even in periods when the results were ambiguous or the progress seemed slow. The astronomers involved had to persuade funding agencies and telescope allocation committees year after year that this work was worth continuing, that the next year's observations would add meaningfully to what was already known, that they succeeded in sustaining this effort over such a long period is a testament not just to their scientific judgment, but to their ability to communicate the importance of what they were doing to the broader community. The result of all that sustained effort was one of the most significant astronomical discoveries of the late 20th century. Confirmation that our own galaxy harbors a supermassive black hole at its center, and that supermassive black holes are not exotic features of distant, unusual galaxies, but a normal and perhaps universal feature of large galaxies throughout the universe. That realization changed our understanding not just of the Milky Way, but of galaxies in general, and of the role that black holes play in the structure and evolution of the cosmos. Chapter 3. The nature of the object, what it actually is. We have established that Sagittarius A-star is a supermassive black hole, but that phrase, supermassive black hole, carries a great deal of weight, and it is worth unpacking it carefully and slowly. What exactly is a black hole? What does it mean for something to be supermassive? And what is actually there at the center of our galaxy when we say that Sagittarius A-star exists? These are questions that deserve more than a quick answer, because the concepts involved are genuinely strange. Strange in the precise sense that they do not resemble anything in ordinary human experience, and cannot be fully understood by analogy with familiar things. We can approach them, we can describe them, we can build up a working understanding of them, but we should not pretend that they are simple, or that the words we use to describe them fully capture what they mean. Let us begin with the most basic question. What is a black hole? A black hole is a region of space where gravity is so intense that nothing, not matter, not light, not any known form of energy or information, can escape from it once it has crossed a certain boundary. That boundary is called the event horizon. It is not a physical surface in any ordinary sense. There is no wall there, no membrane you could touch or see, no line painted across space marking where the black hole begins. It is simply a mathematical boundary, a surface defined by the geometry of space-time in the vicinity of an enormous concentration of mass, beyond which the escape velocity exceeds the speed of light. Since nothing in the known universe can travel faster than light, nothing that crosses the event horizon can ever return to the universe outside. Whatever passes through is, from the perspective of the outside universe, gone forever. This is a remarkable and deeply counterintuitive idea. We are accustomed to thinking of escape velocity as something that depends on how fast you are moving and how hard you try. A rocket can escape Earth's gravity if it moves fast enough. A more powerful rocket can escape the sun's gravity. But near a black hole, past the event horizon, there is no speed that is sufficient. The geometry of space-time itself is curved so severely that all paths, all possible trajectories through space and time, lead inward. There is no direction that leads out. Space, in a sense, is falling inward faster than light can travel outward, and so even light cannot make progress against it. The event horizon is the boundary of that region. Outside it, light can escape, given enough energy and the right direction. Inside it, nothing can. The event horizon is therefore not a place where something dramatic happens to you as you cross it. A traveler falling through it would not necessarily feel anything unusual at the moment of crossing, depending on the size of the black hole. But it is the point of no return, the threshold, beyond which the future contains only the interior of the black hole and nothing else. What lies inside the event horizon is, strictly speaking, unknown. Our best current theory of gravity, Einstein's general theory of relativity, which describes gravity as the curvature of space-time caused by mass and energy, predicts that at the center of a black hole there is a singularity, a point where the density of matter becomes infinite, where the curvature of space-time becomes infinite, where the equations of general relativity cease to produce meaningful results and simply break down. Most physicists believe that this prediction is not a literal description of physical reality, but rather a signal that general relativity is incomplete, that it is an excellent approximation to the truth in most circumstances, but that it fails to describe correctly what happens at the extreme conditions inside a black hole. A complete theory of quantum gravity, a theoretical framework that does not yet exist in finished form, would presumably describe what actually happens at the center of a black hole in a way that does not involve infinities, replacing the singularity with something finite and physically sensible. For practical purposes, when astronomers study Sagittarius A-star, they are studying the region around the event horizon, the space just outside the boundary from which nothing can escape. This is the region where the black hole's gravity is intense enough to be directly observable, where stars are accelerated to extraordinary speeds, where gas is heated to extreme temperatures as it spirals inward under the influence of gravity and magnetic forces, and where the Event Horizon Telescope was able to produce its historic image. Everything we know observationally about Sagittarius A-star comes from this region outside the event horizon. What lies inside remains, for now, beyond observation and beyond the reliable reach of our current theories. The size of the event horizon depends on the mass of the black hole. The mathematical relationship between mass and event horizon radius is one of the simplest in all of physics. The radius of the event horizon, called the Schwarzschild radius, is directly proportional to the mass. Double the mass, and you double the radius of the event horizon. For a black hole with the mass of our Sun, the Schwarzschild radius would be about 3 kilometers. For Sagittarius A-star, with a mass of approximately 4 million solar masses, the event horizon has a radius of roughly 12 million kilometers. That sounds large, and it is, in absolute terms. 12 million kilometers is about 17 times the radius of our Sun, and about 8% of the distance from Earth to the Sun. But relative to the distances involved at the galactic center, and relative to the distances over which the black hole's gravity has a significant influence, it is extraordinarily small. The term supermassive refers to the mass of the black hole relative to other kinds of black holes. Black holes come in a range of masses, and astronomers have identified several distinct categories. Stellar mass black holes, which form when massive stars collapse at the end of their lives, typically have masses between a few and perhaps a few tens of solar masses. They are found throughout the galaxy, the remnants of stars that lived and died over the course of cosmic history. intermediate mass black holes, with masses between roughly 100 and a million solar masses, are thought to exist but are much harder to find and confirm, and their origin is less well understood. And supermassive black holes, with masses from a few 100,000 to tens of billions of solar masses, are found at the centers of most large galaxies, including our own. Sagittarius A-star, at 4 million solar masses, sits at the lower end of the supermassive range. It is vastly more massive than any stellar mass black hole, but modest compared to the largest known supermassive black holes. Objects with masses of tens of billions of solar masses, found at the centers of the most massive galaxies in the universe. The black hole at the center of the giant elliptical galaxy M87, for example, has a mass of approximately 6.5 billion solar masses, more than 1,000 times more massive than Sagittarius A-star, despite M87 being a galaxy of comparable overall size to the Milky Way in some respects. The difference reflects the very different histories and environments of the two galaxies. Where did Sagittarius A-star come from? How did 4 million solar masses of material come to be concentrated at the center of the Milky Way, in a region smaller than the distance from our Sun to the nearest neighboring star? This is a question that astronomers are still working to answer fully, and the honest answer is that we do not yet have a complete picture. The formation and early growth of supermassive black holes is one of the most active and unresolved areas of research in modern astrophysics. Several processes are likely to have been involved in the formation and growth of Sagittarius A-star over the approximately 13 billion years of the galaxy's history. One possibility is that the black hole began as a smaller seed, perhaps a stellar mass black hole formed from the collapse of one of the first generation of massive stars in the early universe, or perhaps an intermediate mass black hole formed from the collapse of a dense cluster of early stars. This seed then grew by accreting gas from its surroundings, pulling in material over billions of years and converting a fraction of it into the mass of the black hole. It may also have grown by merging with other black holes during the many mergers between smaller galaxies that built up the Milky Way over cosmic time. Another possibility is that the seed black hole formed not from a star, but from the direct collapse of a large, dense cloud of gas in the early universe, a process that would bypass the stellar stage entirely and produce a much more massive seed from the beginning. This process, called direct collapse, requires specific conditions that may or may not have been common in the early universe, and whether it actually occurred and how important it was for the formation of supermassive black holes is an active area of theoretical and observational research. What we can say with confidence is that Sagittarius A-star has been at the center of the Milky Way for a very long time, almost certainly for the majority of the galaxy's history. Its gravity has shaped the environment around it, influenced the formation and evolution of the stars and gas in the galactic center, and participated in the overall dynamics of the galaxy in ways that we are still working to understand. It is, in a very real sense, one of the oldest and most enduring features of our galaxy, older than our solar system, older than most of the stars we can see in the night sky, present and gravitationally influential since the early epochs of the Milky Way's formation. It is also, at the present moment, remarkably quiet. A black hole becomes directly observable, produces significant radiation that we can detect, primarily when it is actively accreting material. When gas falls toward a black hole, it does not fall straight in. It has angular momentum, a tendency to orbit rather than fall directly. And so, it forms a swirling disk of material around the black hole, called an accretion disk. As gas in this disk slowly loses angular momentum through friction and magnetic effects, it spirals inward, heating up as it does so, and eventually crosses the event horizon. The heating of the gas in the accretion disk produces radiation, light, X-rays, radio waves, that we can observe from a distance. When a supermassive black hole is accreting at a high rate, the radiation produced by its accretion disk can outshine the entire rest of its host galaxy. These are the objects we call quasars and active galactic nuclei, among the most luminous objects in the known universe, visible across billions of light years. Sagittarius A-star is emphatically not in that state. It is accreting at an extraordinarily low rate relative to its mass, consuming only a tiny trickle of material compared to what an active supermassive black hole would consume. Its luminosity is correspondingly low, far below what even a relatively modest active galactic nucleus would produce. By the standards of supermassive black holes, Sagittarius A-star is essentially dormant, a sleeping giant whose past activity we can infer from indirect evidence, but whose present behavior is quiet and restrained. This relative quietness is paradoxically one of the things that makes Sagittarius A-star so scientifically valuable. Because it is not blazing with intense radiation, the stars and gas in the surrounding region are accessible to observation in a way that would be impossible if the black hole were in an active state. We can track individual stellar orbits, measure the properties of gas clouds, study the detailed structure of the accretion flow, all because the environment has not been cleared or disrupted by the intense radiation that an active black hole would produce. The dormancy of Sagittarius A-star has, in a sense, preserved the laboratory that astronomers need to study it. As you rest with these ideas, let the fundamental strangeness of a black hole settle gently into your awareness, not as something alarming or threatening. Sagittarius A-star is 26,000 light-years away, and its gravitational influence on our part of the galaxy is no greater than that of any other 4 million solar masses of mass at that distance, which is to say, very modest indeed, but as something genuinely extraordinary. An object at the intersection of the very large and the very small, of what we understand and what we do not yet fully grasp, of the familiar physics of gravity and the unfamiliar physics of extreme space-time curvature. One of them sits at the center of our galaxy, patient and ancient, and we are only beginning to understand it. Chapter 4. Scale and Mass. 4 million solar masses. We have mentioned the mass of Sagittarius A-star several times now. 4 million solar masses. It is a number that appears frequently in any discussion of this object, stated almost as a matter of routine in the scientific literature, referenced casually in astronomical papers and presentations, as if it were the kind of number that a person could simply absorb and move on from. But 4 million solar masses is not a number that should be moved on from quickly. It deserves time. It deserves the kind of slow, patient attention that allows a genuinely large idea to settle into something approaching real understanding, even if full comprehension remains out of reach. Let us begin with the Sun. Our Sun is, by any ordinary standard, an enormous object. It has a diameter of about 1.5 million kilometers, more than 100 times the diameter of Earth. If the Sun were hollow, it could contain more than 1 million Earths inside it. Its mass is approximately 2 times 10 to the power of 30 kilograms. Written out in full, that number has 31 digits. It is a quantity so far beyond everyday experience that no analogy drawn from human life can really do it justice. The Sun contains more than 99% of all the mass in the solar system. All the planets, all their moons, all the asteroids and comets and dust and gas that orbit the Sun, everything together, account for less than 1% of the total. The Sun is, in a very direct sense, almost everything that is here. Now hold that in mind and multiply it by 4 million. That is the mass of Sagittarius A-star. Not 4 million times the mass of Earth, 4 million times the mass of the Sun. 4 million of those enormous million Earth objects, each with its 31-digit mass, all concentrated into a single object. The total mass is approximately 8 times 10 to the power of 36 kilograms, a number with 37 digits so far beyond everyday experience that even the comparison with the Sun provides only a partial bridge toward comprehension. What makes this mass even more remarkable is the volume into which it is compressed. The event horizon of Sagittarius A-star, the boundary of the region from which nothing can escape, has a radius of roughly 12 million kilometers. That is about 17 times the radius of our Sun, or about 8% of the distance from Earth to the Sun. In other words, 4 million solar masses of material is concentrated within a sphere that, in the context of the solar system, would fit comfortably between the Sun and the orbit of Mercury. The density implied by those figures, 4 million solar masses packed into a volume smaller than Mercury's orbit, is extraordinary beyond any ordinary frame of reference. One of the most useful ways to develop a genuine sense of what 4 million solar masses means is to think about it in terms of gravitational influence. Gravity extends outward from any massive object in all directions, weakening with the square of the distance. Double your distance from a gravitational source, and the pull is 4 times weaker. At a distance of 1 light-year from Sagittarius A-star, roughly 63,000 astronomical units, or about a quarter of the distance to the nearest star from our own Sun, the gravitational influence of the black hole is still significant. Stars at that distance feel a meaningful pull toward the center. At 10 light-years, the influence is weaker but still present. The gravitational reach of 4 million concentrated solar masses extends across a substantial fraction of the galactic center region, shaping the orbits of stars and the flows of gas across distances that dwarf anything in our local neighborhood. This gravitational reach is what makes the orbits of stars near Sagittarius A-star such powerful evidence for the black hole's existence. We will explore those orbits in detail in the next chapter. But the essential point is this: stars orbiting at distances of a few hundred to a few thousand astronomical units from the center are moving at speeds of hundreds to thousands of kilometers per second. Those speeds can only be maintained by a gravitational field produced by a very large mass concentrated in a very small region. There is no collection of individual stars, no cluster of stellar remnants, no cloud of dark matter that could produce the observed orbits without also producing observable effects that have not been seen. The only explanation that fits all the observations consistently is a single, compact object with a mass of approximately 4 million solar masses, a supermassive black hole. It is also instructive to compare the mass of Sagittarius A-star to the overall mass of the Milky Way. Our galaxy contains somewhere between 100 billion and 400 billion stars, with a total stellar mass of perhaps 50 to 60 billion solar masses. There is also a substantial amount of gas and dust, perhaps another 10 billion solar masses of ordinary matter in various forms, And there is dark matter, the invisible, non-baryonic component that makes up most of the galaxy's total mass, which is estimated to contribute several 100 billion to perhaps 1 trillion solar masses to the total. Against those numbers, the 4 million solar masses of Sagittarius A-star seems almost modest. It represents less than 1/100% of the total stellar mass of the galaxy, a tiny fraction of the whole. And yet, its influence on the galaxy is far out of proportion to its mass, because that mass is concentrated at a single point rather than spread across hundreds of thousands of light years. The gravitational effects of a concentrated mass are qualitatively different from those of the same mass spread out. They fall off more slowly with distance from the center. They accelerate nearby objects to higher speeds. They curve space-time more severely in their immediate vicinity. The concentration of 4 million solar masses into a region the size of Mercury's orbit produces effects that no diffuse distribution of the same mass could reproduce. Thinking about the mass of Sagittarius A-star in relation to other supermassive black holes also provides useful perspective. The black hole at the center of the giant elliptical galaxy M87, the first black hole ever directly imaged in 2019, has a mass of approximately 6.5 billion solar masses. That is more than 1,000 times the mass of Sagittarius A-star. Its event horizon radius is correspondingly larger, about 20 billion kilometers, or roughly 130 astronomical units, larger than the entire solar system out to and beyond the orbit of Neptune. The Schwarzschild radius of the M87 black hole is so large that the orbit of the Earth around the Sun would fit comfortably, inside it with room to spare. At the other extreme, some supermassive black holes are less massive than Sagittarius A-star, with masses of only a few 100,000 solar masses. These are found at the centers of smaller, lower-mass galaxies, consistent with the general trend in which the mass of a galaxy's central black hole scales with the overall mass and velocity structure of the galaxy. The Milky Way, being a relatively ordinary large spiral galaxy, has a relatively ordinary supermassive black hole at its center, not among the largest, not among the smallest, but sitting comfortably in the middle of the distribution. There is something both humbling and reassuring about this ordinariness. Sagittarius A-star is not an exceptional or unusual black hole by the standards of the universe. It is simply the supermassive black hole that happens to be closest to us, the one that anchors our particular galaxy, the one whose gravitational field has been shaping our cosmic neighborhood for billions of years, the one that happens to be near enough for us to study in the detail that proximity allows. Its ordinariness is, in a sense, part of what makes it so scientifically valuable. What we learn about Sagittarius A-star is likely to apply, in broad terms, to the supermassive black holes at the centers of millions of other galaxies across the observable universe. The mass of Sagittarius A-star was not always 4 million solar masses. Black holes grow over time, by accreting gas from their surroundings and by merging with other black holes when their host galaxies collide and merge. The current mass is the result of billions of years of growth, a history that began with a much smaller seed and proceeded through countless episodes of accretion and possibly multiple merger events. The details of that history are encoded in the current properties of the black hole and its environment, but they are not easy to read. Understanding the growth history of supermassive black holes, including Sagittarius A-star, is one of the central challenges of modern astrophysics, and it connects intimately to the broader question of how galaxies themselves form and evolve over cosmic time. For now, let the number 4 million solar masses sit quietly in your awareness. Do not try to fully grasp it. No one can, not really. But let it be large. Let it be heavy. Let it suggest the kind of ancient, patient, gravitational dominance that has been shaping the center of our galaxy since before our solar system existed. 4 million suns, compressed into a region smaller than the distance between our sun and the orbit of Mercury, sitting at the center of everything we call home, holding it all together, turning slowly in the dark. Chapter 5. The surrounding environment, the central parsec. Sagittarius A-star does not exist in isolation. It sits at the center of one of the most complex and active environments in the entire galaxy, a region so densely packed with interesting objects and processes that it has become one of the most intensively studied patches of sky in all of astronomy. To understand Sagittarius A-star fully, we need to understand the environment that surrounds it, not just because that environment is interesting in its own right, though it is extraordinarily so, but because the relationship between the black hole and its surroundings is dynamic and reciprocal. The black hole shapes the environment around it. The environment, in turn, determines what material is available for the black hole to accrete, how active it is, and how it has evolved over time. The two cannot be fully understood in isolation from each other. The central parsec, the region within roughly 3 light-years of Sagittarius A-star, is where the black hole's influence is most directly and immediately felt. A parsec is a unit of distance used by astronomers, equal to about 3¼ light-years, or approximately 31 trillion kilometers. It is a convenient unit for describing distances within the galactic center, where the relevant scales are too large for astronomical units, but too small for the kiloparsecs used to describe the broader structure of the galaxy. Within this central parsec, the environment is unlike anything in the rest of the Milky Way, and understanding it requires setting aside almost everything we know about our own quiet neighborhood of the galaxy. The most prominent structure within the central parsec, visible in radio images of the galactic center, is a feature called the mini-spiral. This is a set of narrow, curved streamers of ionized gas that has been stripped of its electrons by intense radiation from nearby hot stars and from processes occurring close to Sagittarius A-star itself that appear to be flowing inward toward the black hole. The mini-spiral has several distinct components, each named for its appearance in radio maps of the region. There is the northern arm, a curved streamer of gas that arcs inward from the north. There is the eastern arm, approaching from the east. There is the western arc, a more extended curved structure on the western side of the center. And there is the bar, a roughly linear feature that cuts across the inner part of the structure. Together, these components form a loosely wound, 3-dimensional spiral structure that, in radio images, resembles a pinwheel viewed at an oblique angle. The gas in the mini-spiral is moving at high velocities, hundreds of kilometers per second in some parts of the structure, and is being heated to temperatures of thousands of degrees by the intense radiation environment of the galactic center. Some of this gas is almost certainly being accreted by Sagittarius A-star, contributing to the low but non-zero rate of mass accretion that keeps the black hole faintly active. Some of it may be flowing outward rather than inward, driven away from the center by radiation pressure, magnetic forces, or the winds from nearby massive stars. The detailed dynamics of the mini-spiral, which parts of it are flowing inward, which are flowing outward, how it connects to structures farther from the center, and how stable it is over time, are complex and still being worked out by astronomers who specialize in the galactic center. The mini-spiral is not a static structure. It is a dynamic, evolving feature of the galactic center environment, constantly changing as gas flows in and out, as stars move through it and disturb it with their gravity and their stellar winds, and as the radiation environment of the central region fluctuates with the activity level of Sagittarius A-star itself. Surrounding the mini-spiral, at distances of roughly 1 to 7 parsecs from the center, is a larger structure called the circumnuclear disk. This is a ring or torus of molecular gas and dust, cooler and denser than the ionized gas of the mini-spiral, and composed of molecules rather than individual atoms or ions, that orbits Sagittarius A-star at a distance where the black hole's tidal forces are strong but not overwhelming. The circumnuclear disk contains a substantial amount of material. Estimates of its total mass range from a few thousand to perhaps tens of thousands of solar masses, and it is thought to serve as a reservoir from which gas can occasionally flow inward to replenish the mini-spiral and, ultimately, to contribute to the accretion flow onto the black hole. The inner edge of the circumnuclear disk is a region of intense interaction between the cool molecular gas of the disk and the hot ionized gas of the inner region. Gas from the disk that strays too close to the center is ionized and heated by the intense radiation there, transitioning from the cold molecular phase to the hot ionized phase and joining the flow of the mini-spiral. Stars embedded in or passing through the disk region perturb it with their gravity and heat it with their radiation and stellar winds. The whole system is in a state of continuous, complex activity, not violent or catastrophic, but dynamic and energetic in ways that have no parallel in the quiet outer regions of the galaxy. Beyond the circumnuclear disk, at distances of tens to hundreds of parsecs from Sagittarius A-star, the environment continues to be extraordinary by the standards of the broader galaxy. One of the most important large-scale structures in this region is the central molecular zone, a region of unusually dense, warm, and turbulent molecular gas that extends for several hundred parsecs along the galactic plane. The central molecular zone contains roughly 10% of all the molecular gas in the entire Milky Way, despite occupying only a tiny fraction of the galaxy's total volume. This extraordinary concentration of molecular gas is one of the most striking features of the galactic center region, and understanding its origin and dynamics is an important part of understanding the galactic center as a whole. The gas in the central molecular zone is warmer and more turbulent than molecular gas elsewhere in the galaxy. Typical molecular clouds in the outer parts of the Milky Way have temperatures of around 10 degrees above absolute zero and relatively gentle internal motions. The molecular gas in the central molecular zone has temperatures of tens to hundreds of degrees above absolute zero, and its internal velocity dispersions, a measure of the turbulence and disordered motion within the gas, are much higher than in typical molecular clouds. The source of this extra heating and turbulence is not fully understood, but likely involves a combination of strong radiation fields, cosmic rays, shocks driven by supernova, explosions, and the mechanical energy input from the powerful stellar winds of the massive stars concentrated in the galactic center region. Within the central molecular zone, there are several particularly massive and dense molecular cloud complexes that stand out even against the generally rich background of the region. The most notable of these is the SGR-B2 complex, a giant molecular cloud located roughly 100 parsecs from Sagittarius A-star in projection, though the true three-dimensional geometry of the region makes the actual distance uncertain. SGR-B2 is one of the largest and most active star-forming regions in the entire galaxy, containing dozens of sites where new stars are actively being born from collapsing gas clouds. It also contains an extraordinary variety of complex molecules, organic compounds including alcohols, aldehydes, and amino acid precursors that make it one of the richest known repositories of interstellar chemistry in the Milky Way. There is also a remarkable structure called the radio arc, visible in radio images of the galactic center as a series of parallel linear filaments extending perpendicular to the galactic plane over a distance of more than 100 parsecs. These filaments are extraordinarily straight and narrow, running almost perfectly parallel to each other across a region of otherwise complex and turbulent gas. They are thought to trace the magnetic field lines of the galactic center region, lines of magnetic force that are oriented perpendicular to the galactic plane and that are strong enough to organize the ionized gas in the region into these remarkable structures. The strength of the magnetic field implied by the radio arc is much greater than typical interstellar magnetic fields in the outer parts of the galaxy, consistent with the generally more intense and energetic conditions of the galactic center environment. The stellar population of the central parsec is itself a subject of intense scientific interest. Within a fraction of a parsec of Sagittarius A-star, there are stars that should not, by any straightforward application of our understanding of star formation, be there. The tidal forces exerted by the black hole at those distances are so extreme that they would prevent a gas cloud from collapsing under its own gravity to form a star. The outer parts of the cloud would be pulled more strongly toward the black hole than the inner parts, and the cloud would be stretched and disrupted rather than allowed to contract. And yet young, massive stars are found there. Hot, luminous, blue stars that can be no more than a few million years old, orbiting within a fraction of a parsec of one of the most extreme gravitational environments in the galaxy. This is one of the most puzzling aspects of the galactic center environment, and it has resisted a fully satisfying explanation despite decades of theoretical and observational effort. Several mechanisms have been proposed to account for the presence of these young stars so close to the black hole. Perhaps they formed farther away, in less extreme conditions, and were then scattered inward by gravitational interactions with other stars. Perhaps they formed from a disk of gas that was drawn close to the black hole before being disrupted, the formation process somehow managing to proceed despite the tidal forces. Perhaps binary star systems played a role, with one member of a binary being captured into a tight orbit around the black hole, while the other was ejected. None of these explanations is fully satisfying on its own, and the true answer may involve a combination of processes that we have not yet fully worked out. What is clear is that the central parsec of the Milky Way is an environment of extraordinary richness and complexity, one that continues to surprise and challenge the astronomers who study it. Every new observation reveals new detail, new puzzles, new phenomena that require explanation. The region around Sagittarius A-star is not a simple or static place. It is a living, dynamic, constantly evolving environment, shaped by the combined influence of the black hole at its center, the stars that orbit within it, the gas and dust that flow through it, and the magnetic fields that thread through everything. Understanding it fully will require many more decades of observation and theoretical work. But the progress that has been made already is remarkable, and the picture that has emerged, even in its current incomplete form, is one of the most detailed and fascinating portraits of any extreme environment in the known universe. As you rest with this chapter, let the image of the central parsec settle in your mind, not as a collection of facts and structures to be memorized, but as an impression of a place, ancient, dense, active, and deeply strange by the standards of the quiet outer galaxy where we live. A place where gas spirals inward toward a supermassive black hole, where young stars orbit impossibly close to the point of no return, where magnetic filaments thread through ionized gas like threads through a fabric, where molecular clouds the size of star-forming regions shelter complex organic molecules in their cold interiors, while the radiation of the galactic center blazes around them. That is the neighborhood of Sagittarius A-star, and it is, in every sense, extraordinary. Chapter 6. The S-stars and their orbits. The key evidence. Of all the evidence for the existence of Sagittarius A-star as a supermassive black hole, perhaps the most direct and compelling comes from a group of stars known as the S-stars. These are stars that orbit extremely close to Sagittarius A-star, some of them completing full orbits in periods of only a few years, and whose motion has been tracked with extraordinary precision over more than 2 decades of continuous observation. They are, in a very real sense, the key witnesses in the case for the black hole. Everything else we know about Sagittarius A-star, the radio emission, the infrared brightness, the X-ray flares, is suggestive and consistent with the black hole interpretation. But the S-star orbits are what make the case definitive. They are the evidence that close the debate. The name S-stars comes from a simple cataloging convention, S for Sagittarius, followed by a number indicating the order in which individual stars were identified and their motions began to be tracked. There are dozens of them now in the catalogues, each with its own orbit, its own period, its own closest approach distance to the black hole. But among them, one stands out above all the others for the completeness and precision with which its orbit has been measured, and for the scientific weight that orbit carries. That star is S2, sometimes referred to in the UCLA naming convention as S0-2. It has become, in the years since its orbit was first traced, one of the most important individual stars in all of astronomy, not because of anything intrinsic to the star itself, but because of what its motion tells us about what it is orbiting. S2 is a young, hot blue star, what astronomers classify as a B-type main sequence star. It has a mass of roughly 14 to 15 times the mass of our Sun, and a surface temperature of around 30,000 degrees Kelvin, making it significantly hotter and more luminous than our own Sun. By the standards of the galactic center, it is not an unusual object, massive and luminous by everyday standards, but not particularly remarkable for a region that contains many hot, young, massive stars. What makes S2 remarkable is its orbit, and what that orbit reveals. S2 orbits Sagittarius A-star with a period of approximately 16 years. Its orbit is highly elliptical, not a circle, but a stretched oval with an eccentricity of about 0.88, meaning that it is considerably more elongated than circular. At the farthest point of its orbit from Sagittarius A-star, called apoapsis, S2 is at a distance of roughly 10,000 astronomical units from the black hole. At its closest approach, called periapsis, It comes within about 120 astronomical units. 1 astronomical unit is the average distance from Earth to the Sun, approximately 150 million kilometers. So at periapsis, S2 passes within about 18 billion kilometers of Sagittarius A-star, a distance comparable to the outer reaches of our own solar system, close to the orbits of the most distant known dwarf planets. At that closest approach, S2 is moving at approximately 7,800 kilometers per second. To appreciate how fast that is, consider that our Sun moves around the center of the galaxy at about 220 kilometers per second, which is itself an extraordinary speed by everyday standards, fast enough to circle the Earth in less than 3 minutes. S2, at periapsis, is moving at more than 35 times that speed. It is traveling at about 2.5% of the speed of light, one of the fastest moving large objects we have ever tracked in detail anywhere in the universe. The shape and size of S2's orbit, combined with the speed at which S2 moves at different points in that orbit, allow astronomers to calculate the mass of whatever lies at the center of the orbit with extraordinary precision. The calculation uses Kepler's laws of orbital motion, the same mathematical relationships that describe the orbits of the planets around our Sun, combined with the corrections required by general relativity for an orbit this close to such a massive object. The result, from the most recent and most precise measurements, is a central mass of approximately 4.15 million solar masses, confined within a radius no larger than the closest approach distance of S2 itself, and almost certainly within a much smaller volume based on additional constraints from other observations. There is no plausible explanation for a mass of 4 million solar masses confined to that volume other than a supermassive black hole. A cluster of ordinary stars of that total mass would have a radius thousands of times larger. A cluster of stellar mass black holes would be unstable and would rapidly collapse or evaporate. A ball of exotic dark matter would have different observational signatures. The black hole interpretation is not just the most natural explanation. It is, as far as current physics is concerned, the only explanation that is consistent with everything we observe. The observation of S2's orbit has been refined and extended over more than 2 decades of continuous monitoring. The first clear evidence that S2 was following an elliptical orbit around a central mass came in the late 1990s, when enough data had accumulated to trace a significant arc of the orbit. By 2002, S2 had completed nearly a full orbit, and the parameters of that orbit could be determined with considerable precision. In 2018, S2 made another periapsis passage, its closest approach to Sagittarius A-star, and this passage was observed with the best instruments then available, including the gravity interferometer at the Very Large Telescope in Chile, which combines the light from 4 large telescopes to achieve angular resolution far beyond what any single telescope can achieve. The 2018 periapsis passage of S2 was not just an opportunity to refine the orbital measurements. It was also an opportunity to test the predictions of general relativity in the strong gravitational field close to a supermassive black hole. 2 effects in particular were measured and compared with the predictions of Einstein's theory. The first is gravitational redshift. When light climbs out of a gravitational well, when it travels from a region of strong gravity to a region of weaker gravity, it loses energy in the process. This energy loss manifests as a shift in the frequency of the light toward lower frequencies and longer wavelengths, toward the red end of the spectrum. This effect, called gravitational redshift, is a fundamental prediction of general relativity, and it has been measured in many contexts, in light from white dwarfs, in precise atomic clocks at different altitudes on Earth, in the signals from GPS satellites, but measuring it in the strong gravitational field near a supermassive black hole, using the light from a star passing close to the black hole, was something that had never been done before the 2018 periapsis passage of S2. The measurement was made, and the gravitational redshift observed in S2's light at periapsis matched the prediction of general relativity to within the measurement uncertainties. The second effect is the precession of the orbit. In Newtonian gravity, the older, simpler theory of gravity that preceded Einstein's general relativity, a planet or star following an elliptical orbit around a central mass would trace the same ellipse over and over indefinitely, with the orientation of the ellipse remaining fixed in space. But general relativity predicts something different. The orbit itself should precess. The ellipse should slowly rotate in space, so that the point of closest approach moves around the central mass over successive orbits. This precession, called Schwarzschild precession, is extremely small for orbits in weak gravitational fields. It is the same effect that causes the tiny but measurable precession of Mercury's orbit around our Sun, one of the classic tests of general relativity. For S2's orbit, which passes much closer to a much more massive object, the predicted precession is larger and measurable with current instruments. The Schwarzschild precession of S2's orbit was detected and measured in 2020, using data accumulated over more than 2 decades of observation. The measured precession matched the prediction of general relativity precisely, providing another confirmation that Einstein's theory correctly describes gravity even in the extreme conditions near a supermassive black hole. These tests of general relativity using S2 are among the most precise and direct ever performed in the strong field regime. The regime where the gravitational field is strong enough that the differences between general relativity and simpler theories of gravity are large and clearly measurable. Beyond S2, the broader population of S-stars provides additional scientific value. Stars with shorter orbital periods than S2, including S62, with a period of roughly 9.5 years, and possibly others with even shorter periods, come closer to Sagittarius A-star at periapsis and experience even stronger gravitational effects. Tracking their orbits precisely enough to measure those effects is technically challenging, because the stars are faint and closely packed, but it is a goal that current and future instruments are working toward. Stars with longer orbital periods provide complementary information about the gravitational field at larger distances from the black hole, helping to build up a complete picture of the mass distribution in the galactic center region. The random orientations of the S-star orbits, the fact that they point in many different directions with no preferred plane of orbital motion, is itself scientifically significant. In our solar system, all the planets orbit in roughly the same plane, a consequence of the disk of gas and dust from which they formed. The random orientations of the S-star orbits suggest that these stars did not form from a single coherent disk in their current location. Either they formed elsewhere and were scattered into their current orbits by gravitational interactions, or they formed in an unusual way, perhaps from gas clouds that were disrupted and then reformed into stars under the extreme tidal conditions near the black hole, or some combination of both processes was responsible. Understanding the origin of the S stars and the randomness of their orbital orientations is one of the outstanding puzzles of galactic center astronomy, connected to the broader question of how stars form and migrate in the extreme environment of the galactic center. The story of the S stars is, in its own quiet way, one of the great achievements of modern observational astronomy. To track individual stars across 26,000 light-years of space, measuring their positions year after year to within a fraction of a millisecond, following the slow arc of their orbits across the sky over decades. It is a remarkable demonstration of what patient, careful, sustained observation can achieve. The universe does not give up its secrets easily. It requires patience, precision, and persistence. The S stars gave up their secrets slowly, 1 year of data at a time, across more than 2 decades of continuous work by 2 teams of astronomers on opposite sides of the world, using the best instruments their respective generations had available. The reward for that patience was nothing less than a direct, precise, unambiguous measurement of the mass of a supermassive black hole in our own galaxy. Confirmation, written in the motions of stars, that something 4 million times the mass of our Sun sits at the center of everything we call home. It is a result worth appreciating slowly in the quiet of an evening, as the stars that are visible from wherever you are continue their own much more sedate orbits around the same distant center. Chapter 7. The Event Horizon Telescope Image. Imaging the Invisible. On the 12th of May, 2022, the Event Horizon Telescope collaboration released an image that many astronomers had spent years, in some cases entire careers, working toward. It showed a glowing ring of orange and golden light surrounding a dark central region. The ring was not perfectly uniform in its brightness. One side glowed somewhat more intensely than the other, a consequence of the way the hot gas in the accretion region moves relative to Earth, with the side moving toward us appearing brighter due to the Doppler effect and relativistic beaming. And at the center of the ring, clearly visible, was a dark region, the shadow of the event horizon, the area from which no light reaches us, the closest thing to a direct image of a black hole that human technology has ever produced. The image was not a surprise to the astronomers who made it. Theoretical models had predicted, in considerable detail, what the image should look like: the glowing ring, the dark shadow, the asymmetric brightness. What the image provided was confirmation. Confirmation that the predictions of general relativity are correct, even in the extreme conditions near a supermassive black hole. Confirmation that Sagittarius A-star is indeed what the stellar orbits had already told us it was, and confirmation that human ingenuity and technological creativity, applied with sufficient patience and coordination, can reach across 26,000 light-years of space and produce an image of something that emits no light of its own and occupies a region smaller than the orbit of Mercury. To appreciate what that image represents, it helps to understand what the Event Horizon Telescope actually is and how it works, because it is not a telescope in any ordinary sense of the word. It does not look like a telescope. It does not occupy a single location, and it does not produce images in the way that an ordinary camera or even an ordinary astronomical telescope does. It is something considerably more remarkable: a global network of radio observatories spread across multiple continents that are linked together through a technique called very long baseline interferometry to function as a single Earth-sized instrument of extraordinary resolving power. The observatories that contributed to the Sagittarius A-star image were spread across the globe, in Chile, in Hawaii, in Arizona, in Spain, in Mexico, and at the South Pole. Each observatory is a large radio telescope in its own right, capable of detecting faint radio emission from astronomical sources. But when used individually, each telescope has a resolving power, an ability to distinguish fine detail that is far too limited to image the shadow of Sagittarius A-star's event horizon. The angular size of that shadow on the sky is roughly 50 microarcseconds, a microarcsecond being 1/millionth of an arcsecond, and an arcsecond being 1/3600th of a degree. 50 microarcseconds is an angle so small that it is equivalent to the angular size of a golf ball, viewed from a distance of roughly 14,000 kilometers, from one side of the Earth to the other. To achieve the resolution needed to image a feature that small, the Event Horizon Telescope uses the technique of very long baseline interferometry. In this technique, multiple radio telescopes observe the same source simultaneously, recording not just the intensity of the radio waves they receive, but the precise phase and timing of those waves, synchronized by extremely accurate atomic clocks. The data from all the observatories is then combined in a process that uses the interference between signals received at different locations to reconstruct the fine detail of the radio source, in the same way that a much larger single telescope would, in principle, be able to resolve. The effective resolving power of the combined array depends on the longest distance between any two telescopes in the network. And since the Event Horizon Telescope uses observatories spread across the entire surface of the Earth, its effective diameter is the diameter of Earth itself, roughly 12,700 kilometers. The radio waves used by the Event Horizon Telescope have a wavelength of about 1 1/3 millimeters, shorter than typical radio waves, chosen because shorter wavelengths provide better resolution, and because the galactic center is more transparent at these wavelengths than at longer ones. Combined with the Earth-size baseline of the array, this wavelength gives the Event Horizon Telescope an angular resolution of approximately 20 microarcseconds, fine enough to resolve the shadow of Sagittarius A-star's event horizon, which subtends roughly 50 microarcseconds on the sky. Imaging Sagittarius A-star presented particular technical challenges that were not present when the Event Horizon Telescope produced its first black hole image. The image of the black hole in M87, released in April 2019. The M87 black hole is vastly more massive than Sagittarius A-star, 6.5 billion solar masses compared to 4 million. And despite being located in a galaxy roughly 55 million light-years away, rather than 26,000 light-years, its event horizon subtends a comparable angle on the sky, because its greater mass more than compensates for its greater distance. But the M87 black hole's greater mass also means that the structures in its accretion region change on timescales of days to weeks, allowing the observations made over several nights to be combined in a relatively straightforward way. Sagittarius A-star is different. Being much less massive, the timescales for significant structural changes in the gas around it are much shorter, minutes to hours rather than days to weeks. This means that during the hours-long observations needed to accumulate sufficient data for the interferometric reconstruction, the source was changing. The hot gas in the accretion region was moving, flaring, reorganizing itself on timescales comparable to the duration of the observations. This variability made the data reduction and image reconstruction considerably more complex than it had been for M87, requiring the development of new analysis techniques specifically designed to account for a source that does not sit still while you are imaging it. The team addressed this challenge through a combination of careful data selection, choosing time intervals when the source appeared more stable, and sophisticated image reconstruction algorithms that could account for the variability and produce a reliable average image despite it. Multiple independent teams within the collaboration used different methods to reconstruct the image from the raw interferometric data, and the consistency of the results across these different approaches provided confidence that the final image was a reliable representation of the actual source. The image that emerged from this process showed a glowing ring with a diameter of roughly 50 microarcseconds surrounding a dark central shadow. The diameter of the shadow was consistent with the predictions of general relativity for a black hole of 4 million solar masses, matching to within the measurement uncertainties the mass derived from the stellar orbit measurements. This agreement between two completely independent methods of measuring the mass of Sagittarius A-star, one based on the orbits of stars, the other based on the angular size of the black hole shadow, is one of the most powerful confirmations of the black hole interpretation. The image also provides information about the properties of the accretion flow around Sagittarius A-star, the brightness asymmetry of the ring. The fact that one side is brighter than the other is consistent with models in which the gas in the accretion region is orbiting the black hole at a significant fraction of the speed of light, with the approaching side appearing brighter due to Doppler boosting. The detailed brightness distribution around the ring constrains models of the magnetic field structure and the geometry of the accretion flow, and the overall morphology of the image, a ring rather than a more complex structure, is consistent with theoretical predictions for a black hole accreting at a low rate, as Sagittarius A-star is known to do. It is worth pausing to reflect on what the light that formed this image actually experienced on its journey to us. The radio waves detected by the Event Horizon Telescope Array left the vicinity of Sagittarius A-star approximately 26,000 years ago. At that time, our species was in the middle of the last ice age. The great ice sheets still covered much of the northern hemisphere. The ancestors of modern humans were painting animals on cave walls in southern Europe and crossing land bridges between continents. Agriculture had not yet been invented. Cities did not exist. Writing did not exist. The entire recorded history of human civilization, everything from the first cities of Mesopotamia to the present day, fits comfortably into the last 10,000 years of the 26,000-year journey that those radio waves made from the galactic center to our telescopes. And when those waves arrived, they were detected by instruments spread across the surface of a small planet orbiting an ordinary star in the outer reaches of the galaxy that the black hole anchors. Instruments built by a species that has been practicing science for only a few centuries, combined and analyzed using mathematical techniques developed within living memory to produce an image of something that no human eye could ever directly see. That image, a glowing ring of radio emission surrounding a dark shadow, produced by the most extreme object in our galaxy, is one of the most remarkable things our species has ever made. The Event Horizon Telescope image of Sagittarius A-star is not the end of the story. It is, in many ways, the beginning of a new chapter. Future upgrades to the array, including the addition of new observatories in currently underrepresented geographic locations, observations at even shorter wavelengths, and eventually the addition of space-based radio telescopes that would extend the baseline beyond the diameter of Earth will improve the resolution and sensitivity of the instrument, allowing more detailed images of the accretion region, potentially revealing the jets that some models predict, and providing more precise tests of general relativity. The image released in 2022 is the first word in a conversation that will continue for decades. But as a first word, it is extraordinary. A glowing ring around a dark center, 26,000 light-years away, at the heart of our galaxy, seen for the first time by us. Chapter 8. How Sagittarius A behaves. Activity and flares. We have established that Sagittarius A-star is, by the standards of supermassive black holes, remarkably quiet. It is accreting material at a very low rate, producing relatively little radiation compared to the active galactic nuclei seen in other galaxies, and presenting to the universe a face of almost studied calm. But quiet does not mean completely still. Sagittarius A-star is variable. It changes its brightness over time, sometimes dramatically and sometimes subtly, in ways that carry important information about the physics of accretion and the conditions in its immediate environment. Understanding that variability, what drives it, what it tells us about the black hole and its surroundings, and what it implies about the past and future behavior of Sagittarius A-star, is one of the central goals of galactic center astronomy. The most dramatic and well-studied manifestations of this variability are the flares. Several times per day, on average, Sagittarius A-star brightens significantly, by factors of a few in the near-infrared, and sometimes by factors of 100 or more in X-rays, over timescales of minutes to hours. These flares appear suddenly, reach their peak brightness relatively quickly, and then fade back to the quiescent level over the course of an hour or less. They are observed across a range of wavelengths, in near-infrared light, in X-rays, and sometimes in radio waves. And the correlations between flares observed simultaneously at different wavelengths provide clues about the physical processes responsible for producing them. The short duration of the flares, typically less than an hour from start to finish, places important constraints on the size of the emitting region. Because nothing can travel faster than light, a source of radiation that varies on a timescale of minutes can be no larger than the distance light travels in those minutes. For a flare that rises and falls in 30 minutes, the emitting region can be no larger than 30 light minutes across, about 35 times the distance from Earth to the Sun, or roughly the size of the inner solar system. In the context of Sagittarius A-star, with an event horizon radius of about 12 million kilometers, this means that the flares are originating from a region only a few to perhaps a few tens of times the size of the event horizon itself, very close to the black hole, in the most extreme part of the gravitational environment. What causes the flares? This is a question that has occupied researchers for years, and while significant progress has been made, a complete and universally accepted explanation does not yet exist. Several physical mechanisms have been proposed, each with observational support and theoretical motivation, and the true picture is likely more complex than any single mechanism can capture. One of the leading explanations involves magnetic reconnection. In the accretion region close to Sagittarius A-star, the gas is ionized and carries with it a complex, tangled magnetic field. When regions of magnetic field with opposite orientations are brought close together by the motions of the gas, they can undergo a process called reconnection. The field lines snap apart and reconnect in a new configuration, releasing the stored magnetic energy very rapidly. This released energy heats the electrons in the surrounding gas to extreme temperatures and accelerates them to relativistic speeds, producing bursts of radiation across a range of wavelengths. Magnetic reconnection is the same process that drives solar flares on our own sun, though the scales and energies involved near Sagittarius A-star are very different. The magnetic fields are stronger, the densities higher, the velocities greater, and the consequences proportionally more dramatic. Another proposed mechanism involves the formation and orbital motion of hotspots. In this picture, compact regions of unusually hot and bright gas, hotspots, form in the accretion flow close to the event horizon, perhaps as a result of magnetic reconnection or other instabilities, and then orbit Sagittarius A-star at velocities approaching the speed of light. As a hotspot orbits, it moves alternately toward and away from Earth. When moving toward us, its light is blue shifted, and its apparent brightness is enhanced by relativistic beaming. When moving away, it is redshifted and dimmed. This periodic brightening and dimming, combined with the overall evolution of the hotspot as it gradually dissipates, would produce a flare with the observed rise and fall timescales. Evidence for this kind of orbital motion has been seen in high-resolution infrared observations of bright flares, with the emission appearing to trace a roughly circular path around the position of Sagittarius A-star on timescales of about 30 minutes, consistent with the orbital period of gas moving at the innermost stable circular orbit around a 4 million solar mass black hole. The two mechanisms, magnetic reconnection and hotspot orbital motion, are not mutually exclusive. It is entirely possible that magnetic reconnection events create the hotspots, which then produce the observed flares as they orbit. Understanding the detailed relationship between these processes and determining whether other mechanisms also contribute to the observed variability is an active and productive area of research that is likely to benefit greatly from the improved resolution and sensitivity of future Event Horizon Telescope observations. Beyond the short-duration flares, there is also compelling evidence for variability in Sagittarius A-star on much longer timescales of years, centuries, and millions of years. This longer-term variability tells a different and in some ways more dramatic story, one in which Sagittarius A-star was not always as quiet as it is today, and in which the current period of relative dormancy may be just one chapter in a much more eventful history. Perhaps the most striking evidence for past activity comes from a pair of enormous structures called the Fermi bubbles. These are two vast lobes of high-energy gamma-ray emission that extend above and below the galactic plane, stretching from the galactic center to distances of roughly 25,000 light-years in each direction. Each bubble is roughly as large as the entire distance from Earth to the galactic center, a structure of extraordinary scale, visible across a significant fraction of the sky to instruments sensitive to gamma rays. The Fermi bubbles were discovered in 2010 in data from NASA's Fermi Gamma Ray Space Telescope, and their discovery was immediately recognized as one of the most significant findings in galactic astronomy in years. The origin of the Fermi bubbles is not fully understood, but one of the leading explanations is that they were inflated by a past period of much greater activity from Sagittarius A-star. In this scenario, several million years ago, the accretion rate onto Sagittarius A-star was dramatically higher than it is today, perhaps triggered by the disruption and accretion of a large molecular cloud. or by an episode of enhanced gas inflow caused by a close encounter with a satellite galaxy. During this active period, Sagittarius A-star released enormous amounts of energy. Through radiation, through jets of relativistic material launched perpendicular to the accretion disk, or through powerful winds driven off the accretion region. This energy was deposited into the surrounding gas over millions of years, inflating the enormous bubbles that we observe today as the Fermi structures. If this explanation is correct, then Sagittarius A-star was, in the relatively recent past in cosmic terms, a substantially more active and energetic object than it is today. The quiet, occasionally flaring black hole that we observe now would be the aftermath of a more dramatic period, a period during which the center of our galaxy was, at least by the standards of galactic nuclei, genuinely active. The Fermi bubbles would be the lasting record of that activity, slowly fading and expanding over millions of years as the energy deposited by the active phase gradually dissipates into the surrounding gas. There is additional evidence for past activity in the galactic center in the form of what astronomers call light echoes or X-ray reflection nebulae. These are regions of gas near the galactic center, particularly the molecular cloud complex SGR-B2, located roughly 100 parsecs from Sagittarius A-star, that show elevated levels of X-ray emission, with a characteristic spectral signature indicating that they are reflecting X-rays from an external source rather than producing them internally. The geometry of the situation, the location of the reflecting clouds relative to Sagittarius A-star and relative to Earth, allows astronomers to infer that the X-rays being reflected were produced by Sagittarius A-star itself in a burst of activity that occurred several hundred years ago. At that time, Sagittarius A-star appears to have been roughly 1 million times more luminous in X-rays than it is today, still far below the luminosity of a truly active galactic nucleus, but dramatically brighter than its current quiescent state. The picture that emerges from all of this evidence is one of a black hole with a complex and variable history, one that alternates between extended periods of relative quiet and episodes of enhanced activity driven by changes in the supply of material available for accretion. The current quiet period may last for a long time, or it may end relatively soon in astronomical terms, triggered by the accretion of a gas cloud, the disruption of a star that wanders too close, or some other event that increases the flow of material toward the black hole. Predicting when the next period of enhanced activity will occur is not currently possible, because it depends on the detailed dynamics of gas and stars in the galactic center region, on timescales and spatial scales that we cannot yet monitor with sufficient precision. One event that was anticipated with particular interest was the close passage of an object called G2 near Sagittarius A-star in 2014. G2 was identified in 2011 as a compact, red, infrared bright object on a trajectory that would bring it to within a few hundred astronomical units of Sagittarius A-star, well within the region where tidal forces from the black hole are strong enough to disrupt a gas cloud. The passage of G2 was observed by multiple telescopes with great anticipation, with some predictions suggesting that the disruption of the cloud and its subsequent accretion by the black hole could trigger a significant increase in the activity level of Sagittarius A-star, potentially bright, enough to be clearly observable across a range of wavelengths. The anticipated dramatic flare did not occur. G2 passed Sagittarius A-star relatively intact, without producing the strong increase in accretion activity that some had predicted. This outcome suggested that G2 was not a purely gaseous cloud as originally thought, but rather a more compact object, perhaps a star surrounded by a gas and dust envelope, dense enough to survive the tidal forces of the close passage without being completely disrupted. The nature of G2 remains somewhat uncertain, and it has been joined in the catalogues by several similar objects. Compact red, infrared bright sources near Sagittarius A-star, whose nature and origin are not yet fully understood. The behavior of Sagittarius A-star, its daily flares, its past episodes of enhanced activity, its response to incoming material, its long periods of relative quiet, tells us not just about this particular black hole, but about the general processes by which supermassive black holes accrete material, release energy, and influence their environments over cosmic time. Because of its proximity, Sagittarius A-star offers a level of observational detail that cannot be achieved for the supermassive black holes in other galaxies. Each flare that we observe and characterize, each light echo that we trace back to a past outburst, each constraint we place on the accretion rate and its history, adds to a body of knowledge that applies not just to the Milky Way, but to the broader universe of galaxies and the black holes at their centers. The variability of Sagittarius A-star is, in the end, a reminder that even the most extreme and ancient objects in the universe are not static or unchanging. They have histories. They have episodes of activity and periods of quiet. They respond to their environments, and their environments respond to them. The black hole at the center of our galaxy has been there for billions of years, and it will be there for billions more. But in all that time, it has not simply sat still. It has flickered and flared, blazed and quieted, accreted and expelled, shaped and been shaped by the extraordinary environment around it. It is, in its own patient and unhurried way, alive with activity. And we are only beginning to read the full story of what it has done and what it may yet do. Chapter 9. The relationship between black holes and galaxies. One of the most striking and unexpected discoveries of modern astronomy is that supermassive black holes and their host galaxies appear to be deeply and fundamentally connected. This connection was not anticipated. In the early decades of black hole research, it was natural to think of the central black hole as a relatively minor and largely independent component of a galaxy. A curiosity at the center, interesting in its own right, but not something that would have much influence on the galaxy as a whole. After all, the mass of a supermassive black hole is typically only a small fraction of a percent of the total stellar mass of its host galaxy. How could an object so small, relative to the vast structure surrounding it, have any meaningful influence on stars and gas distributed across hundreds of thousands of light years? The answer, as astronomers gradually discovered through the 1990s and into the 2000s, is that the relevant quantity is not mass, but energy. A supermassive black hole accreting material at a significant rate releases extraordinary amounts of energy, not from the material that actually falls through the event horizon, but from the material just outside it, in the innermost regions of the accretion disk, where compression and friction and magnetic effects heat the gas to extreme temperatures. The efficiency with which accretion onto a black hole converts mass into energy is remarkably high. Up to 10% of the rest mass energy of the accreted material for matter spiraling in through a standard accretion disk. Compare this to nuclear fusion in stars, which converts less than 1% of the rest mass energy of hydrogen into energy. A black hole accreting material is, in energy terms, one of the most efficient processes in the universe. This energy does not simply disappear into the black hole. It is deposited into the surrounding gas in various forms through radiation that heats and ionizes the gas, through powerful jets of relativistic material launched perpendicular to the accretion disk along the black hole's rotation axis, and through wide-angle winds driven off the accretion disk by radiation pressure and magnetic forces. The cumulative effect of this energy deposition over millions and billions of years of a galaxy's history can be enormous, large enough to heat gas across the entire galaxy, to drive it out of the galaxy altogether in powerful outflows, and to regulate the rate at which new stars can form from cooling gas. This process of energy feedback from the central black hole to the broader galaxy is called AGN feedback, feedback from active galactic nuclei. It has become, over the past 2 decades, one of the central concepts in our understanding of how galaxies form and evolve. Before AGN feedback was incorporated into models of galaxy formation, those models had serious difficulties reproducing the observed properties of real galaxies. They predicted too many massive galaxies, too much star formation in large galaxies, and gas temperatures in galaxy clusters that were too low. Adding AGN feedback, allowing the central black hole to heat and expel gas, limiting the supply of cold gas available for star formation, dramatically improved the agreement between models and observations. Today, AGN feedback is considered an essential ingredient in any realistic model of galaxy formation and evolution. The observational evidence for a deep connection between black holes and galaxies goes beyond the theoretical necessity of AGN feedback. In the mid-1990s and through the early 2000s, astronomers measuring the masses of supermassive black holes in nearby galaxies, using the same techniques of stellar dynamics and gas dynamics that were being applied to Sagittarius A-star, made a remarkable discovery. The mass of a galaxy's central black hole correlates tightly with properties of the galaxy's stellar bulge, the roughly spherical component of stars at the galaxy's center. In particular, the black hole mass correlates with the total mass of the bulge stars and with the velocity dispersion of those stars, a quantity that reflects how fast the stars in the bulge are moving, and that is related to the depth of the gravitational potential well that the bulge creates. These correlations, known as the M-sigma relation, for the correlation between black hole mass and velocity dispersion, are tight enough to be remarkable. If the growth of the black hole and the growth of the galaxy were independent processes, driven by different physical mechanisms and operating on different scales, there would be no reason to expect such a close relationship between their properties. The tightness of the correlations implies that the two processes are linked, that the growth of the black hole and the growth of the bulge are regulated by the same physical processes, or that one regulates the other through some form of feedback. For the Milky Way, the M-sigma relation predicts a central black hole mass of a few million solar masses, consistent with the measured mass of Sagittarius A-star. The Milky Way has a stellar bulge with a velocity dispersion of roughly 100 kilometers per second, and a black hole mass of 4 million solar masses sits comfortably on the correlation defined by other galaxies. In this sense, Sagittarius A-star is not an unusual or exceptional object. It is exactly the black hole that our galaxy, given its size and stellar structure, would be expected to have. This is both reassuring. It tells us that the Milky Way is a normal galaxy in this respect, and scientifically informative, because it means that what we learn about Sagittarius A-star is likely to be representative of the supermassive black holes at the centers of similar galaxies throughout the universe. The question of how the tight correlations between black hole mass and galaxy properties arise is one of the central unsolved problems of galaxy formation theory. Several mechanisms have been proposed, and the debate about their relative importance is ongoing. One class of models emphasizes the role of AGN feedback in regulating both the growth of the black hole and the growth of the bulge. As the black hole grows, it releases more energy into the surrounding gas, eventually heating the gas to the point where it can no longer cool and form new stars, cutting off both star formation in the bulge and the supply of cold gas for further accretion onto the black hole. In this picture, the tight correlations arise because both the black hole and the bulge are self-regulated by the same feedback process, which naturally drives the system toward a characteristic relationship between their masses. Another class of models emphasizes the role of galaxy mergers in establishing the correlations. When two galaxies merge, their central black holes eventually find each other, spiral together due to dynamical friction, and merge into a single larger black hole. The merging process averages out the properties of the two progenitor black holes and bulges, tending to drive the merged system toward the mean of the correlation, even if the individual progenitors were scattered around it. Over many generations of mergers, this averaging process could maintain the tightness of the observed correlations, even if individual galaxies deviate from them at any given time. The history of the Milky Way is itself a history of mergers. Our galaxy has grown to its current size by absorbing smaller satellite galaxies over cosmic time, and each merger has contributed stars, gas, and possibly black holes to the growing Milky Way. The most significant merger identified in the recent history of our galaxy is an event called the Gaia-Sausage-Enceladus merger. The absorption of a galaxy with roughly the mass of the Large Magellanic Cloud, which occurred approximately 8 to 11 billion years ago, and left its signature in the kinematics and chemical abundances of stars in the Milky Way's halo. This merger likely brought a substantial amount of gas into the galactic center, potentially triggering a period of enhanced accretion onto Sagittarius A-star and contributing to the growth of the black hole during that epoch. Looking forward, the most dramatic event in the future history of Sagittarius A-star is the eventual merger of the Milky Way with the Andromeda Galaxy. Andromeda, also known as M31, is the largest member of our local group of galaxies, a spiral galaxy broadly similar to the Milky Way in overall size and mass, located roughly 2.5 million light-years away. Current measurements of Andromeda's motion indicate that it is approaching the Milky Way at roughly 110 kilometers per second and will begin to interact gravitationally with our galaxy in approximately 4 billion years, with a full merger expected to be complete within perhaps 6 to 10 billion years from now. Andromeda hosts its own supermassive black hole at its center, a black hole estimated to have a mass of roughly 100 million solar masses, approximately 25 times more massive than Sagittarius A-star. When the two galaxies merge, the two black holes will initially be separated by the large distances that separate the galactic centers, thousands of light-years. Over time, dynamical friction will cause the two black holes to spiral toward each other, losing energy and angular momentum to the stars and gas around them. Eventually, when they are close enough, gravitational wave emission will take over as the dominant energy loss mechanism, and the two black holes will spiral together rapidly, merging in a catastrophic coalescence that releases an enormous burst of gravitational wave energy. This merger of Sagittarius A-star with Andromeda's central black hole is billions of years in the future, and the details of how it will unfold are uncertain, depending on factors that include the precise trajectories of the two galaxies, the distribution of gas and stars in both galactic centers, and the spin orientations of both black holes. But it represents the ultimate future of Sagittarius A-star, not the quiet, low-level accretion of today, but a dramatic and energetic end to its existence as a separate object, followed by the formation of a new, more massive black hole at the center of the merged galaxy that astronomers have already named Milky. The relationship between Sagittarius A-star and the Milky Way is therefore not just a relationship of gravitational anchoring, of the black hole holding the galaxy together through its gravity. It is a deeper and more reciprocal relationship in which the history of the galaxy has shaped the history of the black hole, and the activity of the black hole has in turn shaped the evolution of the galaxy. The gas that fell into Sagittarius A-star over billions of years came from the galaxy. The energy that Sagittarius A-star released during its past active periods went back into the galaxy. The correlations between the black hole's mass and the galaxy's stellar structure reflect a long history of coevolution, in which neither the black hole nor the galaxy can be fully understood in isolation from the other. That coevolution is still ongoing. Sagittarius A-star is still accreting, still occasionally flaring, still influencing the environment around it in subtle ways. The Milky Way is still evolving, still forming stars in its spiral arms, still accreting satellite galaxies, still slowly changing its structure over billions of years. The story of the relationship between them is not finished. It is simply at a quiet moment, a long, calm interlude in a relationship that has been eventful in the past and will be eventful again in the future. As you rest with the ideas in this chapter, let the scale of that relationship settle into your awareness. Not just the scale of the distances and masses involved, though those are extraordinary, but the scale of the time. Billions of years of co-evolution between a black hole and the galaxy it anchors. Billions of years of gas falling in, energy flowing out, stars forming and dying, galaxies merging and mixing. All of it connected. All of it part of a single continuous story that began in the early universe and will continue long after our sun has exhausted its fuel and our solar system has grown cold and dark. Sagittarius A-star will still be there, holding things together, patient and ancient and quietly extraordinary. Chapter 10. What we still don't know. We have covered a great deal of ground tonight. We have traced the discovery of Sagittarius A-star from the first radio observations of the galactic center in the 1930s to the Nobel Prize awarded in 2020 and the Event Horizon Telescope image released in 2022. We have explored its nature as a supermassive black hole with a mass of 4 million solar masses. We have examined the extraordinary environment that surrounds it, the orbits of the S-stars that provide the most direct and compelling evidence for its existence, the first image produced by the Event Horizon Telescope, its variable behavior and complex history of past activity, and its deep and reciprocal relationship with the Milky Way as a whole. It has been a long and patient journey through some of the most remarkable science of the past century. But science is never a completed picture. For everything we know about Sagittarius A-star, and we know a great deal, there is much that remains uncertain, unresolved, or entirely unknown. The frontier of our understanding is not a smooth, well-defined line. It is a ragged and irregular boundary, with some areas illuminated clearly by decades of careful observation and others still shrouded in uncertainty. In this final chapter, we will explore some of those areas of uncertainty, the open questions, the unresolved puzzles, the places where our current knowledge runs out and the work of future generations of astronomers begins. The first and perhaps most immediate open question concerns the detailed structure of the accretion flow very close to the event horizon of Sagittarius A-star. The Event Horizon Telescope image produced in 2022 is a remarkable achievement, but it represents only the beginning of what direct imaging of Sagittarius A-star can tell us. The current image shows the broad morphology of the emission region. The glowing ring, the dark shadow, the asymmetric brightness. But it does not yet have the resolution or sensitivity to reveal the fine structure of the accretion flow in detail. Future upgrades to the Event Horizon Telescope array will change this. The addition of new observatories in currently underrepresented geographic locations, particularly in Africa, in Asia, and in the Southern Ocean, will improve the coverage of the interferometric baselines and sharpen the resolution of the images. Observations at shorter wavelengths, where the angular resolution is better and the scattering of radio waves by the interstellar medium is less severe, will reveal finer detail, and the eventual addition of space-based radio telescopes, extending the baseline beyond the diameter of Earth, will push the resolution to levels currently unimaginable. With these improvements, astronomers hope to image not just the overall ring structure, but the detailed brightness distribution within it, the individual hotspots and asymmetries that carry information about the magnetic field, structure, the geometry of the accretion flow, and the properties of the spacetime very close to the event horizon. They hope to detect and characterize the jets that some theoretical models predict Sagittarius A-star should be producing. Collimated outflows of relativistic material launched along the black hole's rotation axis, which have not yet been definitively identified in current observations. And they hope to track the time variability of the image in sufficient detail to follow the orbital motion of individual features in the accretion flow, providing a direct movie of gas moving at a significant fraction of the speed of light in the immediate vicinity of the event horizon. The second major open question concerns the spin of Sagittarius A-star. Black holes in general relativity are characterized by only two quantities, their mass and their spin. The mass of Sagittarius A-star has been measured with considerable precision through both the stellar orbit measurements and the Event Horizon Telescope image. But the spin, how fast the black hole is rotating and in what direction, is much more poorly constrained. Spin matters for several reasons. It affects the detailed structure of spacetime near the event horizon, influencing the size and shape of the innermost stable circular orbit, and therefore the efficiency with which the accretion process converts mass into energy. It affects the launching and direction of jets, if Sagittarius A-star produces them, and it carries information about the history of the black hole, whether it has grown primarily through the accretion of gas in a coherent direction, which would tend to spin it up, or through a series of randomly oriented mergers with other black holes, which would tend to leave it with a more moderate spin. Current constraints on the spin of Sagittarius A-star from the Event Horizon Telescope image are relatively weak. The image is consistent with a wide range of spin values, from nearly zero to nearly the maximum possible. Future, higher resolution images will tighten these constraints significantly, and observations of the orbital motion of hotspots close to the event horizon, which depends sensitively on the spin, may provide a more direct measurement. Determining the spin of Sagittarius A-star is one of the primary scientific goals of the next generation of Event Horizon Telescope observations. The third open question is one we have touched on several times in the course of this evening: the mystery of the young stars in the galactic center. How did massive, young stars come to be orbiting within a fraction of a parsec of Sagittarius A-star? Whether tidal forces from the black hole should prevent the star formation process from occurring? This question has resisted a fully satisfying answer despite decades of theoretical and observational effort. The proposed mechanisms: in situ formation in a disrupted gaseous disk, dynamical scattering from farther out, the Hills mechanism involving the capture of one member of a binary star system, each have strengths and weaknesses, and none of them alone can explain all of the observed properties of the young stellar population in the galactic center. Progress on this question will require both better observations of the young stars themselves, their individual masses, ages, chemical compositions, and orbital properties, and better theoretical models of star formation and stellar dynamics in the extreme tidal environment of the galactic center. The next generation of large ground-based telescopes, particularly the extremely large telescope currently under construction in Chile, will provide the angular resolution and sensitivity needed to characterize the young stellar population in unprecedented detail, potentially resolving the puzzle of their origin, or at least constraining it significantly. The fourth open question concerns the population of stellar mass black holes in the galactic center. When massive stars reach the ends of their lives and collapse, they leave behind stellar mass black holes with masses of a few to perhaps a few tens of solar masses. The galactic center, with its high density of massive stars, should contain a large population of these objects. Theoretical estimates suggest that there may be thousands or even tens of thousands of stellar mass black holes within a few parsecs of Sagittarius A-star. Some of these may be in binary systems with ordinary stars, producing observable X-ray emission as they accrete from their companions. Others may be isolated, detectable only through their gravitational influence on nearby stars, or through the gravitational waves they produce when they occasionally merge with each other, or spiral into Sagittarius A-star. The detection and characterization of this population of stellar mass black holes in the galactic center is an important goal for several reasons. These objects represent a significant reservoir of mass that contributes to the gravitational potential of the galactic center region. Their interactions with each other and with the stars and gas around them influence the dynamics of the galactic center environment. And when stellar mass black holes spiral into Sagittarius A-star, a process called an extreme mass ratio in spiral, they produce gravitational waves at frequencies that will be detectable by the planned space-based Gravitational Wave Observatory LISA, providing a completely new way of studying the properties of Sagittarius A-star and testing general relativity in its strongest known regime. The fifth open question is perhaps the most philosophically profound. What actually happens at the singularity inside the event horizon of Sagittarius A-star? This is not a question that can currently be addressed observationally, since no information can escape from inside the event horizon to reach our instruments. But it is a question of fundamental importance for theoretical physics. The singularity predicted by general relativity, a point of infinite density, where the curvature of space-time becomes infinite and the equations of physics break down, is almost universally believed to be an artifact of the incompleteness of general relativity as a theory, rather than a literal description of physical reality. General relativity is an extraordinarily successful theory in the regimes where it has been tested, but it does not incorporate quantum mechanics, the other great theoretical framework of modern physics, and it is expected to break down at the extreme conditions inside a black hole, where quantum effects on the structure of spacetime can no longer be ignored. A complete theory of quantum gravity, a framework that successfully unifies general relativity and quantum mechanics, would presumably provide a description of what happens inside a black hole that does not involve infinities, replacing the singularity with something finite and physically meaningful. Developing such a theory is one of the greatest challenges in theoretical physics, and several candidate frameworks, string theory, loop quantum gravity, and others have been proposed, but none of them has yet achieved the level of theoretical completeness and observational confirmation that would allow us to say with confidence what happens at the center of Sagittarius A-star. This is not a failure of science. It is simply the current state of our knowledge, accurate and detailed in the regions that are observationally accessible, uncertain and incomplete at the extremes that lie beyond current observation. The history of physics is a history of successively extending our understanding into previously inaccessible regimes, and there is every reason to expect that the current gap at the intersection of gravity and quantum mechanics will eventually be bridged. When it is, the implications for our understanding of black holes, including Sagittarius A-star, will be profound. The sixth open question concerns the future behavior of Sagittarius A-star on astronomical timescales. We know that the black hole has been more active in the past, and we can infer from the properties of its current environment that its future behavior will depend on how much gas and other material is delivered to its vicinity over the coming millions and billions of years. Will it remain as quiet as it is today, accreting at a trickle and producing only modest flares? Or will some event, the disruption of a large gas cloud, the accretion of a satellite galaxy's central gas supply, a close encounter that delivers fresh material to the galactic center, trigger a new period of enhanced activity, briefly transforming Sagittarius A-star into something approaching a low-luminosity active galactic nucleus? The answer is likely yes, that over long enough timescales, Sagittarius A-star will experience additional periods of enhanced activity, separated by long intervals of relative quiet, like the one we are currently observing. The details of when and how are not predictable with current knowledge, depending as they do on the chaotic dynamics of gas and stars in the galactic center region on timescales of millions of years. But the general picture, a black hole that cycles between activity and quiescence in response to the varying supply of material from its environment, is well established from observations of other galaxies and from theoretical models of black hole accretion. There is also the longer-term future of Sagittarius A-star in the context of the eventual merger between the Milky Way and Andromeda, a future we touched on in the previous chapter, in which Sagittarius A-star eventually merges with Andromeda's much more massive central black hole to form a single, larger object at the center of the merged galaxy. That merger, when it occurs, will be one of the most energetic events in the local universe, a release of gravitational wave energy that would be detectable across enormous distances, and a restructuring of the galactic center environment on a scale that would transform everything we have described in the course of this evening. But all of that lies billions of years in the future. For now, Sagittarius A-star sits at the center of our galaxy, quiet and patient, accreting at a trickle, flaring a few times each day, holding the Milky Way together with its gravity and waiting, in the unhurried way of ancient and massive things, for whatever comes next. The open questions that remain about Sagittarius A-star are not a source of frustration. They are a source of anticipation. Each of them represents a direction in which our understanding will deepen in the coming years and decades, as new instruments are built, new observations are made, and new theoretical frameworks are developed. The story of Sagittarius A-star is not finished. It is, in many ways, just beginning. The discoveries of the past century have given us the broad outline of that story. The discoveries of the coming century will fill in the detail, answer the outstanding questions, and almost certainly reveal new puzzles that we cannot yet anticipate. That is how science works, and it is one of the most quietly thrilling aspects of the scientific enterprise. The knowledge that every answer opens new questions, that every advance in understanding reveals new depths of complexity and strangeness, that the universe is always richer and more interesting than our current best picture of it. Sagittarius A-star has been teaching us that lesson for nearly a century, ever since Carl Jansky's rotating antenna first picked up a faint signal from the direction of Sagittarius. It will continue teaching it for as long as we are patient enough to listen. As we bring our exploration to a close tonight, let the full picture of Sagittarius A-star rest in your mind, not as a collection of facts to be retained, but as an impression of something genuinely extraordinary. A supermassive black hole, 4 million times the mass of our Sun, sitting at the center of our galaxy 26,000 light-years away, surrounded by a dense and active environment of stars, gas, magnetic fields, and molecular clouds, revealed by decades of patient observation using radio waves, infrared light, X-rays, and the coordinated signals of radio telescopes spread across the entire surface of the Earth, connected deeply and reciprocally to the galaxy it anchors, shaped by the history of that galaxy and shaping it in return. Quiet now, but with a complex past and an eventful future. Ancient, patient, and extraordinary beyond any ordinary measure. The center of our galaxy has been there since before our solar system formed. It will be there long after our sun has burned out. And at its heart, turning slowly in the dark, a black hole holds everything together, waiting, as it has always waited, for whatever comes next.